Before we begin, please make sure that you have printed out the PowerPoint slides so that you can take notes as we work through some of the theory and the example problems in this section. On your PowerPoint, it's a whole lot easier to understand exponential functions because they're written as f of x equals b to the x. The variable is up in the exponent, and we have some sort of constant value as the base. So we're going to start with one of the most basic, f of x equals 2 to the x. And to build an understanding of this, you know how much I enjoy creating a table of values, but we actually are going to do that here. Start with x, and then evaluate the function, and we'll put in maybe a negative, we'll put in 0, we'll put in a positive, maybe something a little bigger, just to give us an idea about how this function works. So I'm going to start with some of the higher numbers here. If you plug 3 in, 2 cubed is 8, 2 squared is 4, 2 to the first, 2 to the 0 power is 1, and then 2 to the negative 1 turns out to be 1/2. So I'm going to try to plot these points over here. I'll do the best I can. And these start to grow pretty quickly. It's not a quadratic. If we put in more negative values, we're going to get values that get smaller and smaller and smaller, but never actually hit 0 because I keep getting more fractions. So we actually have a horizontal asymptote at 0. So we'll put in a horizontal asymptote right here. So if we have our function, some constant raised to the x, as long as b is positive, we have something called an exponential function. That's our definition. In this slide, we have a whole bunch of facts about our exponential functions. Our domain is all real numbers. Our range goes from 0 to infinity. We never actually start at 0, and we just keep going and going forever. The point 0, 1 is always included. It always crosses right here at 0, 1. And we always have a horizontal asymptote at y equals 0. It's a very nice, continuous, smooth. There is an inverse. It's 1 to 1. If our value of the constant, our base, is greater than 1, we have an exponential growth. That's what we would have over here. If we have a value that's between 0 and 1 in our base, we would have an exponential decay, and our graph is reflected over the y-axis. The properties about crossing where our y-intercept is and our horizontal asymptote, those have not changed. But we can use translations to shift our graph up, down, left, right on our function, and we're going to take a look at that at least a little bit further down the line. So in our exponential functions, base 10 is often used, so 10 to the x shows up a lot. 10 happens to be the base of our numbering system, and base e also happens to show up a lot. These come in quite handy when we get to logarithms and we start talking about the relationship between exponents and logarithms. So let's take a quick look at an example here of an exponential function, and the equation that we have over here we're going to use to talk about the value of a car. So if we wanted to find the value of the car at v of 0, we would plug 0 in wherever we have x, so we would take 25 times 4/5 to the 0. Well, anything raised to the 0 gives us the number 1, so at age 0, year 0, this car is worth $25,000. So a brand new car is $25,000. That's my interpretation after I found it. If I want to sketch it using transformations, all right, first things first, I would sketch my graph. The one spot that I know that this graph crosses is at the ordered pair 0, 1. And I'm going to look at what's in the parentheses. My f of x equals 4/5 to the x. Looking at that function, I have a decay graph. So this might not be the most accurate, but my graph looks something like that. And I'm just going to make my ordered pair bigger, so my graph actually crosses through the point. Then I need to take that and apply some transformations to it. The transformation in front, that 25, does something to my graph, and that's what's going to happen on the next slide. So let's move along over there. So that 25 sitting out in front of the parentheses is called a vertical stretch. And so the question is, how does a vertical stretch change my graph? It originally crossed at 1, and then, kind of sort of did something like this. So instead of crossing at 0, 1, my vertical stretch is going to shift that to 25. So now I have by 5s, 10, 15, 20, 25, we're going to say up here. And bring this down like that. So every single y value is being multiplied by 25. That's exactly what happened with my 0, 1. I originally had a y-intercept, not a y-intercept, a y-asymptote at y equals 0. If I'm multiplying all the y's by 25, that's not going to change over here. I still have y equals 0 as my horizontal asymptote. To look at another real-life example, we happen to have either the heating or the cooling of an object follow an exponential curve using Newton's law, and it probably shows up much better on your screen than it does in mine. It's T of t, so the temperature after time is 70 plus 90 raised to the 90e, and then I think that's a negative, negative 0.1 t in minutes. So at time 0, the question is, how hot was the cup of coffee? And so if I plug in 0, I would have 70 plus 90e to the 0. Anything raised to the 0 is 1, so 70 plus 90 sounds like 160. And this is in degrees Fahrenheit. So my original cup of coffee was 160 degrees Fahrenheit, which is incredibly hot. So we're going to let that cool down a little bit. Now, I want to know what happens to my horizontal asymptote in here. What happens with the 90? What happens with the 70? How does that impact my graph? So I'm going to try to track all of the changes that are taking place to my exponential curve. The original one was e to the t. So that is exponential growth. It would look something like that. Then it goes with this, which is going to turn it from a growth graph into a decay graph, which would make it do something like that. Maybe not quite as narrow or wide, but it, makes it go down. Then I have the 90e to the negative 0.1t, so that multiplication by 90 is a vertical, it multiplies all my y's by 90, so my ordered pair, where it crosses the y-intercept, is now at 0, 90 instead of at 0, 1. And it's still going down like this, but I know where it crosses. Then I added 70 onto it. And my horizontal asymptote stayed at y equaled 0 because multiplying 0 by 90 changed nothing. So by adding 70, that's shifting my graph up 70, which means I now have a y-intercept at 0, 160, and my horizontal asymptote is at y equals 70. So this is my horizontal asymptote. And my interpretation is that that's 70 degrees Fahrenheit. So my coffee is going to cool down, or get closer and closer to 70 degrees. And so I bet that having started at 160 degrees, which is incredibly hot coffee, and going down towards 70 degrees, that this 70 degrees is room temperature. And who wants to drink room temperature coffee? Yuck. Okay, so when I look at f of x here, it looks much nicer on your paper because it's hard for me to tell if the x minus 1 is in the exponent or not. So looking back, I know that it's 2 to the x, and it is x minus 1, and then minus 3 is over here. So I need to know what transformations are taking place here. And I'm taking the function, let me call it h of x. H of x, that would be my original 2 to the x. Then I'm going to transform that using x minus 1 inside the parentheses and then minus 3. So let's see if I can remember what inside the parentheses and outside the parentheses tells me what to do to my function. So if I have x minus 1 inside the parentheses, that's telling me to shift my graph to the, I think that tells me to go to the right. And the minus 3 tells me to go down. 3. So if I can come up with I have a pretty good approximation of 2 to the x. I know that it starts here, goes here, and then I have a horizontal asymptote at y equals 0. It looks something like that. I'm really going to focus on the ordered pair 0, 1. So if I take that ordered pair right 1 and down 3, I would now have my new ordered pair for this function. It would be at 1, no, let's make sure I get that in the right spot. I'm starting at 0, so I'm going over 1. All right, yeah, it's over at 1. And then I was at 1, I'm going down 3, so I'd be at negative 2. And I'm going to do my best to trace just kind of right underneath what I had before. My asymptote is down here, oops, at negative 3, not negative 4. Okay, so the domain, it's all real numbers, and the range goes from negative 3 to infinity.